Tensor analysis, very important subject. These are the introduction and where the tensor come from. And you can see if the material is not isotopic, you can see it's actually create a tensor. These are rotation, so the physical quantity is not going to change if you rotate the frame. So these are rotation to an angle. And these are the new frame of reference, so x1 prime. And you can see the direction cosine. And these are right hand, left hand rule. And you can see contravariant vector is defined this way. The new coordinate is on the top. And covariant vector is defined, the new coordinates at the bottom. And when you do the gradient, you will create a tensor. So this is some brief overview of Riemann geometry. Very important in the relativity. And tensor is major application is relativity. So these are Einstein's equation, and they are all tensor. And non-Euclidean geometry is also important to know. Affine geometry. So these are definition of the second rank tensor. So it's contravariant second rank, you write on the superscript. Mix is one is the superscript, one is subscript. Covariant second rank tensor is subscript. And the operation of the tensor, addition, subtraction, summation. These are the operation. Symmetry and antisymmetry, and the spinor. These are the spinor. These are some examples. And direct product, summation convention, contraction, quotient rule. And these are the fundamental operation with tensor. We will mention about the Minkowski space. And pseudo tensor, dual tensor. These are coordinate system. These are refraction and the inversion, not rotation. And weak interaction is turned out to be a little bit special. These are Levi-Sevier symbol and the tensor density. And reducible tensor. Didactics. Some introduction here. Now we see where it can apply. It's applied to elasticity. So elastic strength, deformation. So these are Taylor expansion. These are Taylor expansion in multiple dimensions. Stress force in the solid. Stress strain relationship is Hooke's law using the tensor method. Generalized Hooke's law is the Hooke's law. And let's see how tensor apply to the Lorentzian covariance of Maxwell equation. Lorentz transformation. Maxwell equation. And we use the curvilinear coordinate, and this how it look like, and this is so-called metric system. Metric. If the Gij is the distance is like a square like this, so ds square like this is called metric. So we can see the Maxwell equation here. Non-Cartesian tensor, covariant differentiation. Let's see how we can do the differentiation. Metric tensor here, raising and lower the indices. This is introduction of curvilinear coordinate. This is some reference. And derivative, Christoph symbol, covariant derivative, tensor derivative operation, diversion, Lagrangian, and curve.